Last month, I was called to inspect a container home in Oregon. The structure had been standing for 18 months. When I arrived, I could see a visible bow in the sidewall, nearly 3 inches of deflection over 40 feet. The owner had cut out 2 full wall sections for windows without adding any reinforcement. I gave them 72 hours to evacuate before I reported it to the building department. 3 days later, during a windstorm, the entire sidewall buckled inward. Total loss, $130,000. I'm a licensed structural engineer, and I've spent the last 12 years analyzing container home failures. What I'm about to share isn't theory. These are the 5 structural mistakes that cause container homes to collapse or fail catastrophically. Every single one of these mistakes is preventable, but every single one can kill someone if ignored. If you're planning to build or modify a container home, this video could save your life. Let's get into it. Last month, I was called to inspect a container home in Oregon. The structure had been standing for 18 months. When I arrived, I could see a visible bow in the sidewall, nearly 3 inches of deflection over 40 feet. The owner had cut out 2 full wall sections for windows without adding any reinforcement. I gave them 72 hours to evacuate before I reported it to the building department. 3 days later, during a windstorm, the entire sidewall buckled inward. Total loss, $130,000. I'm a licensed structural engineer, and I've spent the last 12 years analyzing container home failures. What I'm about to share isn't theory. These are the 5 structural mistakes that cause container homes to collapse or fail catastrophically. Every single one of these mistakes is preventable, but every single one can kill someone if ignored. Here's what most people don't understand about shipping containers. They're not designed to be houses. They're designed to carry weight in a very specific way. A shipping container is engineered to stack 9 containers high when fully loaded. That's 450,000 pounds of vertical load. But here's the critical detail. 100% of that load is carried by the 4 corner posts. Each corner post is a 3.5-inch square steel column with a wall thickness of 6 millimeters. These posts are incredibly strong in compression. They can each handle over 100,000 pounds of vertical load. But the corrugated sidewalls, they carry almost 0 structural load. The walls exist to resist lateral pressure from cargo and to provide racking resistance. They are not load-bearing elements. This is where the catastrophic mistakes begin. People assume that because a container can stack 9 high in a shipping yard, they can stack containers in any configuration for a home. Wrong. In a shipping yard, containers are stacked directly on top of each other with corner posts aligned. Corner post to corner post. Load path is perfect. But in container homes, people want architectural creativity. They want cantilevered sections, offset stacking, and perpendicular arrangements. If you're planning to build or modify a container home, this video could save your life. Let's get into it. Let me give you an example. I consulted on a project where the owner wanted to stack 3 containers in a T configuration. 2 containers on the bottom, 1 on top spanning perpendicular across both. Sounds cool, right? The problem, the top container's corner posts didn't align with the bottom container's corner posts. The engineer they hired initially said it was fine with steel beams supporting the top container. I was brought in for a second opinion after cracks started appearing. Here's what was actually happening. The top container weighed 22,000 pounds. That load was being transferred through 2 steel I-beams into the top flanges of the lower containers. But container top flanges aren't designed to carry concentrated loads. They're 1.5 millimeter sheet metal. Under load, the top flanges were deflecting, creating stress concentrations at the corrugation valleys. Within 6 months, we had fatigue cracks propagating through the steel. The fix required adding vertical steel columns inside the lower containers, directly under the load points, transferring the load down to the corner posts. Cost? $42,000. If they designed it correctly from the start, with aligned corner posts or proper internal framing, it would have cost $8,000. Here's the engineering principle you must understand. Load must travel through the corner posts. If you want to stack containers in non-standard configurations, you must create a structural load path that channels forces into those corner posts. That means internal steel framing, not surface reinforcement. Surface reinforcement doesn't change the load path, it just delays failure. And here's the measurement that matters. If your stacking configuration creates a point load on any surface other than directly over a corner post, you need a structural engineer to design the load transfer system, not a contractor, not a YouTube tutorial. A licensed professional engineer who will stamp the drawings and take legal responsibility. Shipping containers are strong in the vertical direction, but they're surprisingly weak laterally. By laterally, I mean forces pushing horizontally, wind loads, seismic loads, and soil pressure if you're doing a partially buried design. Let me explain the physics. A 40-foot container is a steel tube with corrugated walls. The corrugations run horizontally, which gives the walls some bending stiffness in the vertical direction. But in the horizontal direction, the walls are essentially a series of thin metal waves. When you apply lateral force, the corrugations want to buckle. The container relies on the rigid corner posts and the top and bottom rail frames to resist racking. Here's where people make the fatal mistake. They cut openings for doors and windows, which eliminates the racking resistance. A standard 40-foot container has an effective lateral stiffness of approximately 12 kips per inch when intact. Cut out a 10-foot section of wall for a sliding glass door, you've just reduced the lateral stiffness by 60 to 70% in that direction. I inspected a container home in New Mexico that had 8-foot wide openings cut on both long sides, no structural reinforcement added. The building code in that area required design for 90-mile-per-hour wind loads. I ran the calculations. The container, as modified, could only resist 32-mile-per-hour winds before experiencing permanent deformation. That's a light breeze by structural standards. 6 months after construction, they had a 60-mile-per-hour windstorm. The container twisted 4 degrees along its length. 4 degrees doesn't sound like much, but over 40 feet, that's nearly 3 feet of horizontal displacement at one end relative to the other. Every door jammed, every window shattered. The interior framing separated from the walls. The container was structurally compromised and had to be demolished. The proper solution requires moment-resisting frames or diagonal bracing around all openings. For a 10-foot wide door opening, you need a welded steel portal frame made of HSS tubing, typically 4-inch by 4-inch with 1/4-inch wall thickness. This frame must be welded to the container structure at a minimum of 16 points with full penetration welds, not tack welds. Here are the numbers you need to know. For every linear foot of wall opening, you lose approximately 1 kip of lateral load capacity. To restore that capacity, you need to add bracing with an effective stiffness that matches or exceeds the removed wall section. In seismic zones, that typically means diagonal bracing with a minimum cross-sectional area of 2 square inches and a slenderness ratio below 120. If you're in a high wind or seismic area and you're planning large openings, you need engineered calculations, not rules of thumb, not internet advice. Calculations based on your local code requirements, your soil conditions, and your specific modifications. This is the mistake that terrifies me the most because it's so common and so deadly. Every week I see YouTube videos and Instagram posts showing people with angle grinders cutting massive openings in containers with zero understanding of structural consequences. Let's talk about what you're actually cutting. The top and bottom rails of a shipping container are not decorative trim, they're primary structural members. The bottom rail is a C-channel, typically 6 inches tall and 1/4 inch thick. It ties the four corner posts together and resists torsional loads. The top rail serves the same purpose. When you cut these rails, you fundamentally compromise the container's structural integrity. Here's a real case. A builder in Colorado wanted to create a double-wide container home by placing two containers side by side and cutting out the adjacent walls to create an open floor plan. Sounds reasonable. The mistake, he cut the bottom rails where the two containers met, creating a 14-foot unsupported span. No beam installed, no engineering analysis. For the first year, everything seemed fine, but shipping container steel is Corten steel, which has a yield strength of 50,000 psi but is subject to fatigue under cyclic loading. Every time someone walked across that span, the steel flexed microscopically. After 15 months, we started seeing fatigue cracks at the weld points. By 18 months, one of the cracks had propagated to 6 inches long. I was brought in to assess the damage. The calculations showed that the bottom rail, unsupported over 14 feet, was experiencing bending stresses of 38,000 psi under live load, 76% of yield strength. That's a failure waiting to happen. We had to install an emergency shoring system, then retrofit a structural steel beam. Cost $55,000. Here's the engineering rule. Never cut a top or bottom rail without installing a replacement beam of equal or greater strength. For a 40-foot container, if you're removing a 10-foot section of bottom rail, you need to install a steel beam capable of spanning that 10 feet, plus at least 2 feet of lap on each side for connection. The beam size depends on the loads, but as a baseline, for residential occupancy with a second-story container above, you're looking at a minimum W8 by 15 wide flange beam. That's an 8-inch deep I-beam weighing 15 pounds per linear foot. It must be welded to the corner posts with full penetration welds and designed by a structural engineer. And here's the critical specification. The welds must be inspected. Not visually inspected by the person who did the welding, inspected by a third-party certified welding inspector using dye penetrant testing or magnetic particle testing. 70% of container home structural failures have investigated involved weld failures, welds that looked good but had incomplete fusion or porosity. If you're planning to cut any structural member, corner posts, top rails, bottom rails, or door header beams, you need engineered drawings showing reinforcement details and a qualified welding contractor with AWS certification. This is not optional. This is the difference between a home and a death trap.
Most people understand that steel rusts. What they don't understand is how quickly rust can compromise structural capacity and how insidious the process is. Shipping containers are made of Corten steel, which is designed to form a stable rust layer that protects the underlying metal. That works well in dry environments with good air circulation, but in a container home, especially one with insulation and interior finishes, you create trapped moisture conditions that accelerate corrosion. Here's the mechanism. Moisture gets trapped between the steel and the insulation. It can't evaporate. The steel surface stays wet for extended periods. Normal Corten protective rust layer breaks down and you get progressive corrosion. A corrugated wall that was originally 1.5 millimeters thick can lose 25% of its thickness in 3 years under high humidity conditions. Let me give you the numbers that matter. A corrugated sidewall with 1.5 millimeter thickness has a section modulus of approximately 0.2 cubic inches per foot of width. That section modulus determines the wall's bending capacity. Reduce the thickness by 25% through corrosion, and you don't reduce capacity by 25%. You reduce it by 43%, because bending capacity is proportional to thickness squared. I inspected a container home in coastal Georgia that had been occupied for 4 years. The owner had spray foamed the interior directly against the steel with no vapor barrier. Condensation formed between the foam and the steel. When we removed a section of foam for inspection, we found corrosion had reduced the wall thickness from 1.5 millimeters to 0.9 millimeters. 40% loss of material. The corrugations were flaking apart in my hands. We did a structural analysis. The wall, in its corroded state, could no longer resist the design wind loads. It wasn't safe for occupancy. The fix required removing all interior finishes, abrasive blasting the corroded steel, welding in steel plate patches where corrosion was severe, applying a proper coating system, installing a vapor barrier, and refinishing. Cost $78,000.
Here's how to prevent this catastrophic mistake. First, before you insulate, treat the steel. That means abrasive blasting to remove all mill scale, rust, and shipping contamination. Then, apply a 2-part epoxy primer followed by a polyurethane top coat. Minimum dry film thickness, 6 mils primer, 4 mils top coat. Second, install a proper vapor barrier between the steel and insulation, not plastic sheeting. A closed-cell spray foam with a perm rating below 1, or a fully adhered membrane system. The goal is to prevent moisture from ever reaching the steel surface. Third, design ventilation pathways. Even with vapor barriers, some moisture will migrate. You need air circulation to remove it. That typically means ventilation channels along the bottom and top rails with passive vents or low-speed fans. Fourth, inspect annually. Remove access panels and check for rust. Use an ultrasonic thickness gauge to monitor steel thickness. If you detect active corrosion, address it immediately. Corrosion is progressive, it accelerates over time. The specification that matters. In coastal environments or high humidity climates, your coating system should be designed for a minimum 15-year service life in immersion conditions. That's a higher standard than typical architectural coatings, but container homes trap moisture, so you need industrial-grade protection. The final critical mistake is inadequate connection details between containers and foundations, and between containers and added structural elements. Connections are where loads transfer, and connections are where failures initiate. Let's start with container-to-container connections. Many builders bolt containers together using the existing corner casting holes. Those corner castings are designed for twist lock connectors in shipping applications. Twist locks are fine for temporary stacking, but completely inadequate for permanent structural connections in a building. Here's why. A twist lock connection relies on friction and bearing. Under cyclic loading, wind, thermal expansion, occupant movement, the connection loosens. I've measured bolt tension loss of 60% over 2 years in twist lock connections. Once the bolts loosen, the containers can rack independently, creating differential movement. That differential movement concentrates stress at the connection points. I investigated a failure in Washington State where 3 containers were stacked in an L configuration, connected only with bolts through corner castings. After 2 years, during a moderate windstorm, the connections failed sequentially. The top container shifted 3 inches laterally before friction stopped it. No one was injured, but it was pure luck. The proper solution requires welded connections. For container-to-container stacking, you need a minimum of 4 welded connections per corner, each with a minimum 3-inch weld length. The weld must be a fillet weld with a minimum 1/4-inch leg dimension using E70 series electrodes. That provides a shear capacity of approximately 2,100 pounds per inch of weld. But here's what people miss. The weld quality matters more than the weld size. A poorly executed 1/2-inch fillet weld is weaker than a properly executed 1/4-inch fillet weld. I've seen beautiful-looking welds that had 0 penetration, just melted metal sitting on the surface. That's not a weld, it's decoration. Proper weld specifications require qualified welders working to AWS D1.1 structural welding code. The welds must be visually inspected for undercut, overlap, porosity, and crack indications. For critical connections, anything supporting occupied space above, you need non-destructive testing. That means ultrasonic testing or radiographic testing of 10% of welds. Now let's talk about container-to-foundation connections. This is where I see the most egregious mistakes. People set containers on concrete piers and assume weight alone will keep them in place. In a seismic event or high wind, a 20,000-pound container can slide, uplift, or overturn. The engineering requirement is positive anchorage. For wind uplift, you typically need to resist forces of 3,000 to 6,000 pounds per corner, depending on your exposure category and building height. For seismic loads in high-risk zones, you can see lateral forces of 8,000 pounds or more. Proper anchorage uses embedded anchor bolts or post-installed anchors with a minimum diameter of 5/8 inch embedded at least 7 inches into concrete. The anchor must be designed for combined tension and shear. You need a minimum of 2 anchors per corner post, positioned to create moment resistance. Here's the failure case. A container home in California was set on concrete piers with no anchorage. The owner assumed the weight was sufficient. During a 5.4 magnitude earthquake, the container slid 6 inches off its supports. The gas line ruptured. The owner was lucky. The gas shutoff activated before ignition, but the container was rendered uninhabitable and the foundation was damaged. Repair cost? $96,000. The specification that matters: your container to foundation connection must be designed for the greater of 110% of dead load in uplift or the calculated wind or seismic uplift force. The connection must be detailed on engineered drawings and installed by qualified contractors. Let's review the 5 critical structural mistakes that cause container homes to collapse or fail. Mistake 1: improper load distribution. Load must travel through corner posts. If you're stacking in non-standard configurations, you need engineered load paths. Mistake 2: inadequate bracing and lateral support. Every linear foot of wall opening removes 1 kip of lateral capacity. You must restore that capacity with moment frames or diagonal bracing designed for your wind and seismic loads. Mistake 3: cutting structural members without reinforcement. Never cut top rails, bottom rails, or corner posts without installing replacement beams of equal or greater strength, with full penetration welds inspected by certified welding inspectors. Mistake 4: ignoring rust and corrosion. Treat steel before insulating. Install vapor barriers. Design ventilation pathways. Inspect annually. Corrosion can reduce structural capacity by 40% or more in just a few years. Mistake 5: poor connection details. Use welded connections for container-to-container joints. Use positive anchorage for container-to-foundation connections. Specify AWS D1.1 welding standards and require third-party inspection. Every one of these mistakes is preventable. Every one requires engineering analysis, and every one can result in catastrophic failure if ignored. If you're serious about building a container home that's safe, that meets code, and that will stand for decades, you need to work with licensed professionals. That means a structural engineer for load analysis and connection design, a qualified welding contractor with AWS certification, and third-party inspections to verify the work was done correctly. I know engineering fees seem expensive. A typical container home structural engineering package costs $5,000 to $15,000. But compare that to the repair costs I've described today: $40,000, $50,000, $90,000, or worse, compare it to the cost of a structural failure that injures or kills someone. If this video has helped you understand the critical structural issues in container homes, I need you to do 3 things. First, hit that subscribe button. I release detailed engineering content every week that will help you avoid these costly and dangerous mistakes. Second, turn on the notification bell so you don't miss any videos. Third, visit the link in the description to access our free foundation calculator. This tool will help you determine the proper foundation system for your soil type and container configuration. Next week, I'm releasing a deep dive video on container insulation systems and why 90% of DIY insulation jobs are failing within 5 years. You need to see that video before you insulate your container. Thanks for watching. Build smart, build safe. And remember, structural engineering isn't expensive. Structural failure is.
Here are 5 common mistakes. Second, no rollback plan. Third, and more handoffs. Always follow the solutions.